doing? All right. Hello, friends. Let's talk about rational equations again. You might have asked the other day, maybe, as we were doing rational functions, you might be thinking in the back of your mind, what real-world applications are there? I hear you say, and I'm here today to help you answer that question. I'm the kind of guy I am. Okay? I'm always there for you. Okay. So we'd like to think about, in particular, two situations among many that one could have, where rational equations naturally arise. So let me show you. First, we'll have two slides, two examples. Let's talk about concentration first. And here's my very, very technical definition of concentration. Do you like it? Amount of, actually even a more loose definition would be amount of stuff you care about divided by the total amount of stuff, right? That would be like the idea of concentration. I'm not sure I even need to hand you a formula to like say that, but you know, there you go. Often we're doing problems like the following where it's like we're talking about acid or something. So I don't know why. We're always like interested in mixing acids and things. So makes things exciting. Yes, it's your crazy lab here. And as soon as we talk about concentration, really another word for concentration would be like ratio, right? We're just really talking about the ratio of the thing we care about to the total amount of stuff, right? So with that description in mind, it's just a ratio. I think you can already see all the way through this a little bit. I think you can see how a rational function might possibly naturally arise in this context if we're like dealing with ratios. Okay. And in general, that's how you'll get ratios in life, won't you? Is like rational functions. Is when you're dealing with things that like, you're thinking about ratios. So let's first start by, if you haven't read this problem yet, let's come up with a concentration function for this situation. And let's let x, it says how much pure acid must be added. And in math, if there's like something that someone is asking you and you don't yet know it and you desire eventually to know it, let's let that be the unknown. So let's let x be the volume of acid added. All right, and then I'd like to come up with like a formula for the concentration regardless of what x you pick. Okay. Let's start with the denominator since I think it's somewhat easy. Remember that the denominator is just the total amount of stuff, period. We started with a total of 50 milliliters, and we've added how much stuff? If we've added, yes, good. You've added x stuff. And notice I don't even care whether that stuff is acid or water or Kool-Aid or mud. It doesn't matter. We had 50 milliliters of stuff, and you've added x milliliters of stuff. So the total amount of stuff is 50 plus x. Wonderful. Now the numerator is a little bit trickier. Now the question is how much stuff is there of the stuff we care about? So at your table, work that out.
That is 35%. And that, instead of trying to get C, it's like 5%.
If you guys could put all your test folders into one pile, I'll come around. While you're talking about this, I'll come around and grab it.
At the beginning, it's not fast.
You grab the numerator? Did come up with the numerator? And then when you're ready, you can actually solve the problem, right? You haven't yet solved the problem too. All right. Let me Let me hear from, how about Alexis? Did you guys get the numerator?
Okay, so
Hey, guys.
kind of thinking that you should get 35% of 50.
Okay, so what do I write?
So, point, you write that.
35% of 50.
Oh, it's okay, so 0.35 times 50.
Okay.
Yeah. That's about as far as you got.
Okay, that is in fact the amount of acid that is originally in the mixture before we do anything else. You guys agree? Yeah. Great. And then add x. You guys agree with that? Okay. You guys agree with that? Okay. By the way, so I think we're good. By the way, this could be, we could change the problem in a number of different ways. Just so you know, there's like, this is the general principle, but you're not always going to have this like structure all the time necessarily. Here we're adding, the numerator is always increasing. The numerator, excuse the denominator, and the numerator is always increasing too because this is the amount of acid, isn't it? So this is the initial amount of acid, and we're adding pure acid. So I think this makes sense at any given time that this will calculate meaningfully the concentration after X milliliters of acid has been added. Oh, just the dot thing. Sorry. Yeah. This one actually I think you could do for the most part without a calculator, but I might give you a calculator. Yeah. Yeah, we'll do that here now. We're looking for when is the concentration 0.75 is what the question actually asks. So we'll solve that equation now. Keep in mind though, before you go and solve that, I just want to make sure you understand that like this situation could come up in other ways. How would you change this formula if you were adding water instead? Certainly the volume would be going up of the whole mixture still in exactly the same way. But how would the numerator change? What if we were adding always a mixture of like 50% water, 50% acid to this? And that's always the mixture we were adding to this. How would that change the numerator? All right, so I'm just saying, you think about this general principle as you solve this. Okay, so go ahead and solve this if you haven't already. Tell me what you get.
No.
No? All right, what'd you get for x? Did you solve it just using algebra? Are you done yet? No, you're not done yet. We'll hear from Allie what she says. Whatever Allie says the answer is, that's the answer. Even if you think it's wrong, it's Allie says the answer. That's going to be the end of the story. What'd you say? 80, is it right? Doesn't matter. Allie said it. It's 80, okay. 80 milliliters. Good. We'll assume that the algebra in the between looks beautiful. I'm sure it does. I decided just for fun to graph our function, c of x. Here it is in y1. I put it in my calculator. What window would be appropriate in this context? Keep in mind the context of the problem. X? What's x represent? Yeah, so it only makes sense for x to be positive. So how about 0 to how many milliliters we care about? Certainly, you know, maybe we're adding 100 or something. We already have a good idea because we solved this question too. All right, whatever. Y? What about y? 0 would be a good bottom for y. And 1, how about, would be 100%, wouldn't it? Okay, so let's see what this looks like. Is that what you expected it to look like? Yeah, I mean, the concentration is going up, so I think that makes sense. What feature of the graph would you like to talk about? There is a feature of the graph that's interesting. By the way, we could trace this. If we go to 0, we have 0.35, is that what you expected? Isn't that the concentration originally at when you haven't added any acid? What other feature of the graph do you see? What's going on? It's not just going uphill, it's also, what else do you want to say? What happens as you put in like tons and tons? What's the long range behavior of this as you put tons and tons of acid into this? What is the concentration approach? Yeah, it approaches 100%, doesn't it? So what are we claiming about the graph then? It has a horizontal asymptote, and what's the horizontal asymptote? Y equals 1. Can you connect that back to the algebra too? If you look at the actual function expression, does it have a horizontal asymptote of 1? Yes. Okay. And in the real world context, it makes sense that the concentration could get arbitrarily close to 1, couldn't it? So that makes good sense. What would it be in that situation where I said where if you were to continually add 50% water, 50% acid mixture, if you were to just add buckets and buckets of that? Well, eventually it would approach 50%. And like, who cares that there's like, oh, there's 50 milliliters of this original solution that had some other mixture. If you've just added like millions of milliliters of water, 50% solution, then it'll approach obviously 50%, right? So think about the long-range behavior and how this connects back to things we know and love from before. Oh, one more thing there too. If you wanted to solve this on the calculator, you could also graph the line y equals 0.75 and find that the intersection is at x equals 82, right? Of course. You didn't do that though. It sounds like most of you did the algebra. Okay, one more, so we can get one more example out here before we go on, before we leave you today. Let's talk about average cost. And again, I have a very simple equation, and I refuse to explain it to you until we look at this problem. Okay, let's look at this problem, and then immediately you'll understand the real-world value of thinking about this idea of average cost. Okay, so we've got this lemonade stand. It's got this catchy name, Lemon Life. Okay, I made that up. You're welcome. Okay, and you are paying $500 initially to just like get started in this business. This is not just your average roadside lemonade stand. We have a state-of-the-art lemon squeezing machine. We have beautiful pictures and equipment. And we have professional graphic design produced signage. Very, very, very high quality. We're going for yeah, life-changing, that would be a good name for this business too. Life-changing lemonade. We're going to set it up in some of the higher-end neighborhoods in this county, okay? It also costs, we also incur a cost of 20 cents per cup for production cost of the lemonade. Like there's obviously an ongoing cost here, isn't there too? Right? We don't ever have to buy the lemon squeezing machine again, but we do need to like continually buy lemons and water and whatever else. Something. I don't know. Maybe you don't even have to buy that. You just got that from the tap. I don't know. Yeah, you're set up next to a fire hydrant. You know? All right. So let's write a function for the average cost. Apparently, it's this. It's the total cost divided by x. So use your Algebra 1 skills to come up with a numerator for me. What's the total cost of producing, in total, startup cost and... You got it. Look at that chorus of great answers. Okay. Great. So now what does this actually mean? I want to plug a number in and make sure you understand what this gives us. It's actually a really useful function. Right? So but what do we mean by average cost? Imagine you were to set up your business, produce exactly 10 cups of lemonade, and then shut down the business. The question is, how much did it cost on average to produce each cup of lemonade? How expensive was that per cup, right? And the answer is, well, if you plug 10 in, you get 502 up top, right? Over 10. So that's $50.20 per cup of lemonade. If you start a business, make 10 cups only, and then shut down business, right? You average a cost per cup of $50.20. Do you see how that's a really useful thing to think about? Now, 10 cups is clearly not a great amount to produce. Well, what about 1,000, right? Does it start to be more reasonable then? This is the question. In fact, I have a bigger question here. What if we'd like to charge $1 a cup eventually? Right now, if we only produce 10 cups, then we need to be selling them for like $50.20 or more in order to recoup our costs, yeah? which maybe would go in some places in this county. I don't know. But we'd like to charge, we think the market can bear $1 a cup. That's what we think. So the question is, when will the average cost dip below $1? Right? When will this be worth it for me and for my customers here? When can I make that happen? So solve that equation equal to 1, and we'll get a number of cups here. Yeah. Yeah. I mean, this is the way someone in the real world would probably word it, right? So let's answer it our way, and maybe we can disagree on the answer. Go ahead. What'd you get? 625. Yeah. So at 625, I think that's correct. Cups. Your profit would be exactly 0, wouldn't it? Like if you make 625 cups, it actually costs exactly $1 on average, $1 per cup to do it. So if you sold all 625 cups, then that'd be good. So maybe 626 cups, and after we would actually be making a profit. And as you leave, what's the long run cost, average cost? What's the long run average cost going to be? As we produce millions of cups. It'll go down to what? No. 0.2. Yeah. All right. Asymptotes in the real world. That's what we're doing here.